get to it and add it. Okay, so last class we ended off around here and we talked about what a buffer is. A buffer is a solution that contains a weak acid and its conjugate base, or you could say a weak base and its conjugate acid, right? So we're talking about weak base and weak acid together. And why do we need to have both an acid and a base in a buffer solution? The reason why you want to have both of these is because if you add a strong acid to a buffer, it's going to react with the base, right? It's going to consume the base and produce more of the weak acid. If you add a strong base to your buffer, it's going to react with the acid, right? It's going to react with the acid. So a buffer in that way can neutralize both strong acid and strong base. Now, the most ideal buffer that you can make is one where you have the concentration of the weak base and the weak acid in a ratio of about 1 to 1. Okay, so a ratio of 1 to 1 of both the weak acid and weak base are ideal because it can resist the addition of strong base or acid equally. It doesn't matter if you were to add, 10 milliliters of whatever concentration of strong acid, or if you did the same thing with strong base, it can resist pH changes in either direction. Now, if we rearrange our equilibrium constant, and if we were to add some strong, if we rearrange our Ka expression here, you can see that when we have the most ideal buffer, again, when the relative concentration of the acid and the base are equal, it's supposed to be canceled out here, you see that at that point, again, when you've created a buffer where the concentration of the acid and the base are identical, you can see that the pKa is going to be equal to the pH of that buffer. Okay, so if you know the pKa of the weak acid, there you go. You know the pH of the buffer. Similarly, if you rearrange it for the Kb expression, and again, if the concentration of the weak acid and weak base are identical, you're going to find that the pOH is going to be equal to the pKb. Okay, so there we go. Anyhow, again, to maximize buffering capacity, the pH of the solution, we want it to be roughly equal to the pKa of the acid, right? Okay, there we go. Well, again, we talked about this last class, what buffering capacity is. It's the amount of protons, which is strong acid, or hydroxide ions, which is strong base, that the buffer can take on without a significant change in pH. And I tried to stress this with you a lot during the last class. Just because you have a buffer doesn't mean there's going to be no change in pH. It just means there's not going to be a large change in pH. Again, the capacity of the buffer depends on the concentration of the weak acid and weak base. Greater the concentration, greater the buffering capacity, okay? So if you had a concentrated buffer, you're going to have more of the weak acid and conjugate base than you would in a dilute buffer. And a concentrated buffer is going to be able to withstand changes in pH upon greater addition of greater amount of strong acid or strong base. Well, how is the pH of a buffer going to be affected, right? We talked about how the concentration of acid or base is going to be affected when we add strong acid or strong base to a buffer, but what impact is it going to have on the pH? If we rearrange our Ka expression and we solve for H3O+, remember in chemistry, the H3O+, right, concentration, we can just replace that with H+, okay? If you solve for the concentration of the strong acid, it's equal to Ka times Ha divided by the concentration of A-. If we take the negative logarithm of both sides, we end up with this equation right here. Let me prove it to you. If you have the concentration of your acid is equal to Ka times Ha over A-, like that. If you take the negative logarithm of both sides, what do you get? You get the negative log of the concentration of H+ is equal to the negative log of Ka plus the negative log of concentration of Ha over A-, like that. What's the negative log of H? It's pH. What's the negative log of Ka? It's pKa. And I can rearrange this because I know that the negative log of HA over A minus is going to be equal to the positive log of A minus over HA, like that, okay? It's going to be equal to plus the log of A minus over HA. And there you have it. That is the Henderson-Hasselbalch equation. If you don't follow me on this right here, let me prove it to you. If you had, and this is something that I'm sure most of you know, but I just want to be 100% sure, if you had the log of 2 over 1, okay, it's going to be equal to the negative log of 1 over 2. Look, if you take your calculator and you take 2 and you take the log, you get 0.30, pardon my language. If you take the log of 0.5, you get negative 0.30. So if you have the negative of that, you end up with 0.30. And that is how we rearrange to get the Henderson-Hasselbalch equation. So when you're dealing with a buffer solution, the pH is equal to the pKa plus some kind of tuning factor based on the leftover concentration of conjugate base and acid after the neutralization has occurred. All right? Keep in mind that the Henderson-Hasselbalch equation is very powerful. However, it can only be used for buffered solutions. So you can't just throw it out there for any solution under the sun. It has to be a buffered solution. If you want a little bit of practice in deriving the Henderson-Hasselbalch equation, you could try deriving it for a base as well. And you'd see that if you take your weak base and you put it in water, and there's nothing here that you don't know already, we get our conjugate acid plus hydroxide, like that. So we could write our Kb expression is going to be equal to the concentration of our conjugate acid times the concentration of hydroxide divided by the concentration of our base. Okay, and there's more than one way to do this. Okay, you can solve for the concentration of OH minus, which is going to be equal to Kb times the concentration of the base divided by the H plus, like that. We take the negative log of both sides. We get the negative log of the concentration of hydroxide, which is equal to the negative log of the Kb plus the negative log of the concentration of B over the concentration of the conjugate acid. Same thing as last time. Negative log of concentration of hydroxide is POH. Negative log of Kb is PKb. And then we can simplify this to plus the log of BH plus divided by concentration of B. And so there's the Henderson-Hasselbalch equation expressed for calculating POH. All right, I'm going to skip question 37 for now so that we can get into section 14.7, which deals with titrations and pH curves. So titration, as one of my students said, titration, I looked at titrations last semester. Well, we do cover titrations in General Chemistry 1. However, the titrations that we cover in General Chemistry 1 only deal with strong acids and strong bases being titrated, okay? We don't deal with any weak acids and weak bases, and that is a big part of what we learn in Chapter 14 in General Chemistry 2, is we spend most of our time, if you think about it, focusing on weak acids and weak bases. So probably a lot of this will be a review to you, but it says titration is a technique that's used to determine the concentration of an acid or base solution. We have what's called a titrant, which is our strong acid or base that's of a known concentration, and the titrant will be in our burette. And then we have the analyte, which is what we're trying to determine the concentration of, and we have that in an Erlenmeyer flask so that we can swirl it, right, while we're doing the titration. If you're in Chemistry 14-12 right now and you're doing the labs in person, I'm sure that you're getting a chance to try your hand at titration, no pun intended. So in titration, a measured amount of strong acid or base is added to the analyte, and we monitor the pH. How do we monitor the pH? We monitor it with something called an indicator. In the indicator, we usually only need to put 1 drop of the indicator. So the volume of the indicator is essentially negligible. Now, if you're wondering what the heck is an indicator is something that's going to change color at a certain pH where what's called the equivalence point is going to be reached. Now, if you're wondering what the equivalence point is, we're going to cover that in a little bit. But right now, I want to take a look at what would happen if we titrated a strong acid with a strong base. This, again, is something that you probably would have seen in chemistry 1401. In general chemistry 1, you did talk about titrations of strong acids and strong base. So I've worked the whole thing out. You can see there's a lot of math here, but follow me and it won't be that bad. Okay, we're going to take it step by step. Okay, and trust me, this one looks more complex than it is because we're just dealing with strong acids and strong bases. Okay, let's say you have a solution of 0.10 molar HCl, okay, and you've got 40 milliliters of it. Then what you're going to do is you have that in an Erlenmeyer flask, and you're going to titrate it with 0.20 molar sodium hydroxide. Okay, so what it's saying is that your HCl in that sample problem is in here, and your sodium hydroxide is in here. And what you're going to do is you're going to monitor the pH as you add varying amounts of sodium hydroxide to that HCl. Might sound complicated at first, but again, it's a strong acid and strong base, so it's simpler than when we look at weak acids and weak bases, which we will in a minute. So what's the pH at the very beginning when you've added no sodium hydroxide? Well, you've got a 0.10 molar solution of HCl. HCl is a strong acid. It's going to dissociate completely. So the pH is simply going to be equal to the negative log of the concentration of my HCl. Here I wrote out the whole equation. I'm sure that most of you don't even have to write that out by now. You say, look, it's a monoprotic strong acid. I know my pH is going to be equal to the negative log of the concentration of that acid. And we get that our pH is 1. It makes sense because all we have is hydrochloric acid. We don't have anything else in there. But what would happen if we added 18 milliliters of sodium hydroxide? Well, I'm given the concentration of my sodium hydroxide, aren't I? I know that I have 18 milliliters. I just converted that into liters, multiplied by the concentration, and I get that I have 0.0036 moles of sodium hydroxide being added. How many moles of HCl am I starting with? Well, I've got 40 milliliters of a 0.10 molar solution. So I work that out. Again, I convert the milliliters to liters by dividing by 1,000, and I get 0.0400 liters multiplied by the concentration gives me this many moles. Now what's happening here is we have a reaction between a strong acid and a strong base that are in a 1-to-1 stoichiometric ratio. So since there is less of the sodium hydroxide, it's going to get completely consumed so that you'll be left over with none, and you're going to consume that many moles of the HCl, so you'll only be left over with a little bit of the HCl. Now you're also going to form a sodium and a chloride, but we have discussed this in detail that these are not going to affect pH when we discussed ions that affect pH and ions that don't affect pH. So therefore, in this mixture, after this first step, or step number 2, you've got water, sodium ions, chloride ions, and HCl. You don't have any sodium hydroxide left over. But how would I calculate the pH? The only thing in there that's going to affect the pH will be the concentration of the HCl. Okay, that's the only thing, right? So now it's just a strong acid, and it's going to ionize completely. Well, what's the concentration of that hydrochloric acid? This is where you've got to be careful. I've seen students make this mistake many times. They'll say, well, I have the number of moles of HCl. I'm going to divide it by my 40 milliliters. Well, hold on. What's the total volume of the solution? Right? Total volume in this step, total volume is going to be equal to 40.00 milliliters plus the 18 milliliters from the sodium hydroxide, 18.00 milliliters, which is going to give you 58 milliliters, which is going to be equal to 0.05800 liters. So I divide that, I get the concentration of my strong acid that's left, my hydronium. And so you take the pH of that, and when you calculate the pH, you see that it's gone up from 1 to 2.6. Does that make sense that the pH would be increased? Absolutely, because you've already neutralized some of the strong acid. You've got less strong acid in there now. Okay, give me a thumbs up if you follow me that far. All we've done is we've added some sodium hydroxide, but we still just have HCl left over that ionizes. Anybody with me? Okay, cool. Thanks, Shannon. Yeah, so all we've done thus far is this step and this step. Now you can imagine that the reason that I have these volumes is for a good reason, right? I didn't just choose these at random. I chose them to kind of try to teach you something along the way. Okay, well, what's going to happen if we add 20 milliliters of sodium hydroxide, right? We're going to do this exact same setup. If we have 20 milliliters of sodium hydroxide multiplied by the molarity, what do we get? We get 0.0040 moles. Well, hold the phone. That's exactly how much HCl we had. So that means our HCl is going to be completely neutralized. It's going to be gone. Look, you got no HCl left over. Okay? So what you have left over is you're going to form sodium ions and chloride ions. Those don't change the pH of the solution. And therefore, you're going to be at a pH of 7. Why? Because you don't have any strong acid or strong base left over. You've only got water and sodium and chloride ions. All right, so our pH is completely neutral, right? And we call this the equivalence point. So again, when the titrant, or the HCl in this case, has been completely neutralized, we call that the equivalence point. All right, give me a thumbs up if you follow me on equivalence point. It's when all of the acid has been neutralized. And of course, since we're a strong acid and a strong base, all we have is water and sodium chloride. It's not going to increase or decrease the pH. It's going to be completely neutral. Okay, here's where it gets more interesting. Now what's going to happen, we've done this part, if we add a whole crap load more of sodium hydroxide, we're adding 5 more mils, right? We're adding a total of 25. What do you think is going to happen to the pH? If at this point we were at the equivalence point and the pH was equal to 0, the pH was equal to 7, and we're adding more sodium hydroxide, the pH should skyrocket, shouldn't it? Because now all you're going to have left over is just sodium hydroxide, pure sodium hydroxide. Let's take a look. So we have our 0.00, and it's not written in here, but our 0.0040 moles of HCl, and we're adding this many moles of sodium hydroxide. So that means all the HCl is going to be consumed, but we're going to be left over with this much sodium hydroxide, aren't we? That many moles. We're also forming some sodium and chloride ions, but again, we don't care about those because they don't affect the pH. All right, what's the concentration of our sodium hydroxide? It's going to be this many moles divided by the total volume. What's the total volume? 40 milliliters plus 25. That gives me 65 milliliters. So I divide by 0.0650 liters. I get the concentration of my sodium hydroxide. You know that sodium hydroxide is a strong base. It ionizes completely to give you sodium ions and hydroxide ions. The concentration of my hydroxide ions is going to be 0.015 molar, right? So I calculate the POH, which gives me 1.82. Since pH is equal to 14 minus POH, we get that the pH skyrockets. It goes way up to 12.18 because what do we have left over? Nothing more than strong base. So if you go back to your general chemistry, what you would have solved for in there would have been probably just one of these. They would have given you one, just said, okay, what happens at this point or something like that, right? That's the kind of thing, or it would have asked you to determine the concentration of the sodium hydroxide. But that's not the purpose here. The reason why we want to look at what happens at all of these different steps, step 1, 0 mils, 18, 20, 25, it's because when we're looking at the titration of a weak acid with a strong base, we want to look at a similar stepwise approach, and you're going to see that it gets a little more interesting, okay? Things are a little more complicated. But what would the titration curve, or what's called the titration curve, look like for this titration of a strong acid and a strong base? Well, I can tell you that I've looked at the ACS final exam enough to know that you have to be able to recognize this curve, okay? If you see this If you see this curve walking down a street, okay, you've got to be able to point at it and say, hey, wait a second, that's a strong base with a strong acid. Okay, so the way that the titration curve works is that you have pH on the y-axis and you have the volume of the titrant added over here. So if my line, if I read it from left to right, just like you read prose, okay, or the English language, if I start on the left-hand side, you can see that my pH is really low. That tells me I'm starting it with what? A strong acid. If my pH is below 2, you better believe that's a strong acid, okay? You bet your bobby socks that's a strong acid. But then what happens is that the curve becomes vertical or almost vertical. What does that mean? That means that the pH is increasing dramatically until it reaches the equivalence point. Now, again, when we titrate a strong acid and a strong base, the equivalence point is at a pH of 7. And then after the equivalence point has been reached, you're just throwing base in there, and of course, you're going to have a really high pH. So the features of this curve that you have to be able to recognize, again, strong acid titrated with a strong base, is that the curve is symmetrical around the equivalence point. At the equivalence point, the pH is going to be neutral, 7. The pH rises very sharply around the equivalence point. And a good indicator, remember I told you that you put an indicator in the Erlenmeyer flask, and we'll talk about indicators more. You usually put just 1 drop of your indicator. There's my pipette, okay? You're going to put 1 drop of indicator in there. A good indicator is one whose pH range is in the vertical line of the curve. Well, you can use a whole holy host of pH indicators here because the vertical part of the curve is pretty damn big, okay? And you're like, Mr. Dion, that's not vertical. That's got a slope to it. Okay. Throw me a bone here. It's pretty damn vertical compared to this and this, isn't it? Okay, so you can see the vertical point of the curve, or part of the curve, covers a large range of pHs, all the way from around 3 to 11. And so there are many different pH indicators out there, and we're going to look at some at the very end of the lecture. But again, a good indicator has to be in the range of the vertical line of the curve. Anyhow, there we go. Well, let's look at something a little more complex, okay? Just going to move my desk here. Just give me 2 shakes of a lamb's tail. We're going to talk about the titration of a weak acid or a weak base, and we're going to titrate it with a strong acid or a strong base. I know there's a lot of text on here, but follow me and we'll take it one step at a time, and I think it will become relatively clear to you from the beginning. Okay, how the hell is this going to be different? If you're like, come on, Mr. Dion, it's just an acid and a base. What's the difference? Okay, you just went through acid and a base. Why is it different? The difference is this. Even if you don't understand what it is yet, when you're dealing with weak acids and weak bases, right, it's calculating pH isn't as clear, is it? We have to look at Ka values or Kb values. So here we go. The reason why it's more complicated, the titration of a weak acid or a weak base, is because after the neutralization reaction is complete, remember when we did it with a strong acid and strong base, what did we end up with? Sodium, chloride, water, stuff that we didn't care about at all. If you neutralize a weak acid or a weak base, you're going to end up with something that will affect the pH, right? You can end up with a weak acid or a weak base, okay? So that means it turns into a 2-step problem. If you still don't follow me, watch carefully. Look, we're going to go over both scenarios here. First, you're going to determine the concentration of everything that's left over after the neutralization. Okay? So, of course, you assume no ionization of the weak acid or weak base. So let's say you added a strong base, okay, to a weak acid, and you neutralized all the strong base. When you do that, you're going to produce weak base, aren't you? Right? Because remember, I told you that when you add a strong base, I said the pH is going to increase. Not a lot, but it will increase. Who's causing it to increase? It's the conjugate base. So therefore, you have to evaluate the new concentration of your weak acid and your weak base, and then you've got to solve using Ka, which we've done, what, 100 times just in lecture? Okay? The same thing would happen here if we had a strong acid being added to the base. You destroy the strong acid by a neutralization, but now you're going to have some conjugate acid and some of the base left over. So now you're going to have to use KB. Sorry, I wanted to use a green highlighter. Now you're going to have to use this expression and use KB. So it's a two-step problem, okay? It's a little more complicated. All right, now I know I've got a lot of text on here. I completely am fully aware of that. But I want you to follow me very carefully. It's similar to the last one, but it's not the same because now we're going to titrate 0.10 molar acetic acid. Acetic acid is a weak acid. Acetate is the conjugate base of acetic acid, okay? So we're going to titrate 40 mils, just like we did the last time, so the same number of moles, and we're going to titrate it with a strong base. All right, what's going to be the pH of 40 mils of 0.1 molar acetic acid when you have no sodium hydroxide added? Come on. You're like, give me something difficult, Mr. Dion, right? Just write out a nice table, okay? Solve for X the same way that we always did. We make our assumption the same way that we always do, and we solve for the concentration of X, which is the concentration of hydronium, and we measure the pH. We have done this, 100 times might have been a stretch. I'm going to say 15 times in lecture we've done this exact same exercise, okay? So that is really nothing new under the sun. I'm not saying it's easy. I'm not saying it's a joke or anything like that. I'm just saying we've done it a lot. So here's where it gets more interesting. What's the pH after you've added 5 milliliters of sodium hydroxide? So this is where it gets drastically different from the titration of a strong acid and a strong base. Follow me. You're adding this many moles of sodium hydroxide. Again, we just multiply concentration by volume, right? And you have this many moles of acetic acid. You're going to consume all of the sodium hydroxide because there's less of it than there is acetic acid. So we subtract this much. We're going to subtract the same amount here, and we're going to gain that amount of acetate. The reason I'm not going to talk about the sodium a whole lot is because it doesn't change anything, does it? Okay, the concentration of sodium affects diddly squat. So at equilibrium, we have this many moles of our acetic acid. So HOAC, that stands for acetic acid, HOAC, and OAC minus, that stands for acetate, so that's the conjugate base. It's just a shorthand, okay? You've got this many moles of the conjugate base. You know what the total volume is? 40 plus 5, so 45. You figure out the concentration of each. You make an ice table, just like we always do. You assume that X has no effect, and you solve for X, which gives you the concentration of the hydronium, and you evaluate the pH, which is shown down here. Okay? Give me a thumbs up if you're like, I follow you part of the way, Mr. Dion, even if you're with me half of the way, because I know I'm doing a lot of talking, but I want to get into solving a problem like this. Is everybody with me? First, you do the neutralization. Then you write it in a nice table for your weak acid and weak base. Same thing we've done hundreds of times. If you're wondering, where the hell are you? Look, I'm just doing this first, the neutralization, and then just a Ka or a Kb, okay? Stuff we looked at a bunch of times. Okay, so what's going to happen if I add 10 mils of sodium hydroxide? All right, let's work it out. Now it gets interesting because I've got the same number of moles, I have this many moles of my sodium hydroxide, and I have this many moles of my acetic acid. So I'm going to lose this many here, so I'll be left over with no strong base. But look what happens is you're going to subtract that many moles of acetic acid, and you're going to gain that many moles of acetate. So you're going to have the same number of moles of weak acid and weak base. Now hold on a second. I remember something about the Henderson-Hasselbalch equation. Wait a second. Let me write that down. pH was equal to pKa plus the log of the concentration of A minus over HA. Hold the phone. If I have the same number of moles of both of these, that means they're going to have the same concentration. That means that I'd be taking the log of 1, which is 0, and that means that the pH should be equal to the pKa. You don't even have to do that table, right? You know, based off of the Henderson-Hasselbalch equation, that if you want to make an ice table, be my guest. You know, this is the land of the free. But if you've got the same concentration of weak acid and weak base, this part is going to cancel out, and the pH is going to be equal to the pKa. So you just take the negative log of the Ka of acetic acid. Okay, we call this the half equivalence point. You see here it says half EQPT. That means the half equivalence point. Okay, half of the analyte has been neutralized, and at the half equivalence point, we just drew a tasty conclusion, which is pH is equal to pKa. Oh, I like that, right? Who likes things to be simpler? Me, okay? So I like any trick that I can learn to simplify my life. Okay, so that was step 3. Now in step 4, we're going to add 20 mils of sodium hydroxide. Oops, where the hell am I? There we go. 20 mils. So we're going to add some more sodium hydroxide. So 20 mils. Now look at this. You've got the same number of moles of sodium hydroxide that you do acetic acid. That is the equivalence point. When all of the titrant has been neutralized. Now, close your eyes and imagine this. When we looked at the equivalence point between a strong acid and a strong base, the pH was 7, wasn't it? All you had was water and sodium chloride in our example. Here, it's not that simple, because you're not making water and sodium chloride. You're making water and sodium and the conjugate base of acetic acid, which is going to affect the pH. Sorry, I'm slamming my hand on the desk here. But anyhow, so now you've got 0.004 moles of this, and you're going to figure out its concentration right here. You're going to make a nice table, and since we're using the base, we're going to calculate the Kb. Right? We're just going to use Kb. It's going to be equal to x squared divided by 0.067. Instead of calculating the Kb, when I made this slide, I actually just wrote it here, wrote it out instead of actually putting it in there. In 1 times 10 to the negative 14 divided by 1.8 times 10 to the negative 5. So my pKb, or my Kb, is equal to 5.6 times 10 to the negative 10. Look, the assumption is totally safe. 0.067 is much greater than 5.6 times 10 to the negative 8, right? And 100 times the Kb value. Okay? You calculate for x, which is the concentration of OH. You take the pOH and you measure the pH like that. All right? And then lastly, there's one more scenario. Okay? It's not over yet. I promise we're almost there. Okay? The last scenario is, what if you have more than enough? Like you've got more than enough sodium hydroxide. There's an interesting assumption here that I know will be abundantly clear when you see it, but you have to see it from your instructor, or you have to read it in the book. So look, if you have too much sodium hydroxide, right, more than enough, well, you're going to be left over with a little sodium hydroxide in the end, but you're also going to be left over with the weak base, okay? Yes, sodium ions, but we don't care about those. Here's something that you've got to remember, okay? If you're not awake, wake up just for a second, okay? If you've got some sodium hydroxide, if you've got some sodium hydroxide in some of this, you don't have to worry about this at all. It's not that it's not, well, it's not important for our calculation, because if you have a strong base and a weak base mixed together, the only one that's going to affect the pH is going to be the strong base, okay? The concentration of hydroxide from the strong base is going to be way more than from the weak base, okay, because you don't have to consider a Kb for a strong base. So you only consider the strong base concentration. Got this many moles, okay? You know the total volume, which is 65 milliliters in this case. You get pOH and you calculate pH, okay? Looks like a lot of steps, is it? Absolutely. And what would our titration curve look like? Again, if you see this curve walking down the street, say you're in downtown Colorado Springs, you see somebody walk by with a t-shirt with this on it, you've got to be able to recognize that. You're like, well, it looks like the last one. It looks the exact same. Let's go back. It's not exactly the same. This one is perfectly symmetrical around a pH of 7. Let's go back here. Again, we're titrating a weak acid with a strong base. Okay? It's not completely symmetrical. How would you know if you just saw that picture with no heading? How would you know it's a weak acid and a strong base? Well, first of all, the pH is above 2. It's starting above 2, so that tells you it's a weak acid. When it was below 2, then we knew it was a strong acid. So we know we're starting with a weak acid, then we're titrating it, and then we know it's a strong base because we're ending up with a pH above 12. All right, so that's the titration of a weak acid and a strong base. This portion here is a buffer range, okay? Now, it depends on your instructor. Dr. Diaz, I don't know if any of you know Dr. Diaz, but he's my best friend, and he also teaches this class, and he and I are on the same page in 98% of the things that we teach. Some things we differ on the way we do it. Now, this range here is the buffer range. So in the buffer range, you can use the Henderson-Hasselbalch equation, okay, in the buffer range. If you are uncomfortable doing that, so he always tells his students, just use the Henderson-Hasselbalch equation if you've got a buffer. Well, I've taught this class long enough that I've seen many students get confused. They're like, is this a buffer, or if not, or is it not a buffer? If you're ever confused about that, just use an ice table, okay? You can never go wrong by using an ice table. At least I think you make less mistakes that way, okay? Then we get in here to the equivalence point, okay? What is the pH at the equivalence point? It's not 7, is it? The pH is above 7. It's basic, right? Okay, at the equivalence point, the pH is above 7. You have a basic equivalence point. Why would that be? Because at the equivalence point, you've neutralized all the weak acid with strong base, but what did you make? You made weak base, and weak bases are basic. And so you're going to have a basic pH at the equivalence point, okay? And then after that, once you've added too much hydroxide, well, then it's just POH, right? So the typical features of this curve, I went over the pH at equivalence point. Before the equivalence point, that's the buffer region. After the equivalence point, the pH skyrockets really quickly. The curve is not symmetrical. And the half equivalence point, if you really want to get down to the nitty gritty, I showed you what the half equivalence point, that's when you have an equal concentration of weak acid and conjugate base. I told you that the pH is equal to, right? At the equivalence point, pH is equal to pKa. It's the volume of the sodium hydroxide needed to reach the equivalence point divided by 2. You don't have to have that memorized, but if you have it in your back pocket, it can help you. It can get you out of a bind, okay? Anyhow, so the equivalence point is that point where you have enough titrant that's added to neutralize all of the acid or the base that's being titrated. And it's defined by stoichiometry, okay? The equivalence point is not defined by a pH, okay? Depends on the situation, right? You saw the equivalence point of a strong acid and a strong base had a pH of 7. The pH, when we titrated a weak acid with a strong base, the equivalence point was not 7. It was above 7, okay? So again, equivalence point is not always going to be a pH of 7. This, I just put that in here because I've seen students make that assumption before, okay? Which is a dangerous assumption to make. All right, I noticed that I had used this slide before, and I didn't like the way this is written. This should say ammonia. So let's try question 38. What time is it? It's 10:06. We got 3 hours left. So let's see if we can blast our way through this problem. Camden, do we have 3 hours left? All right. All right. Thanks, Camden. Good. We got 3 hours remaining. I'm just teasing you guys. Anyhow, I wish we did. I really enjoy doing these kinds of problems. Look, if you know, when I was going over this, all these different steps here, and you're like, whoa, that is so many numbers. That is so much information, Mr. Dion. I'm overwhelmed. Look, if you learn how to do this, not only will I promise that it be rewarding, but you're going to realize that it's a step-by-step approach. Okay? It's nothing new. It's just looking at the amounts of acid or base that are added to a weak acid or weak base. That's all. Okay? So let's take a look at question 38. Let's see if we can figure it out. It says you get 10 milliliters of 0.10 molar ammonia. Ammonia is a weak base. They give you a beautiful Kb value. Thank you. Okay? You're titrating it with some hydrochloric acid. Hydrochloric acid is a strong acid. So this is the titration of a weak base with strong acid. Something we haven't even looked at yet, right? Spoiler alert. There's my spoiler, right? And the curve here. We'll look at it later, okay? Let's try the problem first and see if we can figure out what the hell is going on. Pardon my language. Okay. What is the pH when you've added none of the acid? You're like, come on, give me something challenging, Mr. Dion. I know that if I have ammonia and I put it in water, based off of Bronsted-Lowry definition, ammonia is a weak base. It's going to be a proton acceptor. It's going to accept a proton to form an ammonium ion and hydroxide. Okay? I know what the concentration of my ammonia is. It's 0.10 molar. Molar. I know my Kb. It's given to me. It's 1.8 times 10 to the minus 5. Hey, look, this concentration is much bigger than 100 times my Ka. So I'm going to be able to make an ice table really quick and makes the assumption that X isn't going to have any effect on the concentration of my ammonia. There we go. Come on. Give me something difficult. Right? I've done this 100 times. X squared over 0.10 is equal to 1.8 times 10 to the negative 5, right? Kb is equal to X squared over 0.010. That's all. I'm just simplifying it a little bit. And so X is going to be equal to the square root of 1.8 times 10 to the negative 6, just doing a little tiny bit of mental math, okay? That's the concentration of my ammonium ion, but it's also the concentration of my hydroxide. And so that is going to be equal to 1.3 times 10 to the negative 3 molar. My POH is going to be equal to the negative log of 1.3 times 10 to the what? Negative 3. I get that my pH, sorry, my POH is equal to, what did you guys get? I got 2.87. 2.87. And so my pH is going to be 14 minus that. It's going to be 11.13. Okay, that's my pH. It's basic. It's not above 12 though. So we know it's a weak base. Okay, we solved the first part. Done. Now what's going to happen if we add 5 mils of hydrochloric acid? Well, if in my buffer solution I have ammonia and I have ammonium ions in my buffer solution, or sorry, not my, if I'm sorry, I get too many things in my brain here. If I'm adding hydrochloric acid, it's going to get neutralized by my base. So let's write out what's going to happen. I gave myself lots of room here to work on this problem. So my ammonia is going to react with the hydrochloric acid to produce ammonium ions plus chloride ions. What makes these problems more complex than the titration of a strong acid and a strong base? And if you're like, Mr. Dion, are you repeating yourself? Yes. Okay. Is that, you have weak base and conjugate acid. So we're going to have to do a double ice table here. Okay. So initially, we are starting out with how much ammonia? We have 0.10 moles per liter multiplied by the volume, which is 0.0100 liters. The number of moles that we have is 0.0010 moles. So that's initial. The amount of HCl that we've added is 5 milliliters. So we have 0.10 moles per liter multiplied by 0.00500 liters. Okay, and we get that the initial amount of our HCl is 0.0005. There's less HCl than there is ammonia. And so all of that HCl is going to get consumed. We're going to lose all of it. Okay, and we're going to lose some of the ammonia. And we're also going to form some ammonium. And we're going to form some chloride. I don't really give a crap about the chloride, but anyhow, I'll write it in there because I'm the teacher. Okay, at equilibrium, we're going to have 0.000. I'm going to put an extra sig fig in there because we've got to have at least 2. We're going to have no HCl, and we're going to have 0.00050 moles of this, 0.0050 moles of this. The only two players that I'm interested in are my ammonia and my ammonium ion. That's all I give a crap about. Now, I'm going to calculate the concentration of both of these. I take my 10 milliliters, right? 10 milliliters, and I added 5. So I've got 15 milliliters. So I divide this by 0.0150 liters, divided by 0.0150 liters. You probably notice what's going on here. The concentration at equilibrium is going to be equal to 0.033 molar, and here it's 0.033 molar. Look, the number of moles, or the concentration of my ammonium and my ammonia, are identical. So I am at, this is at the half equivalence point. You're like, how do you know that? Because at half equivalence point, the concentration of ammonia should be equal to the concentration of the ammonium. Now, you've got two options. You can either make an ice table here, which I'm not going to do. I think it's in my solutions. Yes, we're working on 2. Yes, okay. We're in this part right here. We've added 5 milliliters, right? 5 milliliters of HCl, okay? So I can use the Henderson-Hasselbalch equation. pH is equal to pKa plus the log of the concentration of the conjugate base. Just do it like this, of my ammonia divided by the concentration of my ammonium ion, and they're identical. The log of 1, you guys know what the log of 1 is? Try it. Take your calculator and put 1 log, and you get 0. And so pH is going to be equal to pKa. They gave me the pKa, or they gave me the Kb, and so the same thing is also true, that we know that the pOH is going to be equal to the pKb. Kb. And so we can say our pOH is going to be equal to the negative log of, what was our pKb? Or Kb? It's 1.8 times 10 to the negative 5. So let me just work this out here. 1.8 times 10 to the negative 5. Boom. We get our pOH is equal to 4.74. And so our pH is going to be 14 minus 4.74. We get that our pH is equal to 9.26. Now, does this make sense? Do you guys follow me on the Henderson-Hasselbalch equation here? That we're at the half equivalence point. It's a definition, right? The concentration of base and acid, weak base and weak acid, are identical, and so they cancel out, so the pH is equal to the pKa. Give me a thumbs up if you follow me on that, because I have another point that I want to make. Thanks, Shannon. All right. Food, very good, okay? Being silly because I think it's because it's Friday and I'm excited. So Joel asked me, where did I get that 1.8 times 10 to the negative 5? Did I say, Joel, that that was equal to my Kb? Oh, yeah, I get it right here. The Kb. Does that help, Joel? Okay, cool. Okay. So look, I had one more point I wanted to make. Mr. Dion has lots of points here, right? Now let's just make it simple. Okay, let's keep going. So now we're going to add 10 milliliters of HCl and see what happens. Okay, same old steps over and over and over, right? Okay. Look, if you're confused, it's rocking your world, just watch. Do it slowly. We've got some ammonia, right? You're going to add some HCl to it. That's going to produce an ammonium ion plus fluoride. The fluoride doesn't matter a hill of beans because it doesn't affect pH. How much ammonia did we start with? We worked it out in the last one, so I'm just going to write it out here. You're starting out with 0.0010 moles. We already know that. Now, if I'm adding 10 mils of my 0.1 molar HCl, you're multiplying 10 by 0.1, so you're going to end up with the exact same amount. So you have 0.0010 moles. Okay, again, all I did was the number of moles is equal to the concentration in molarity times the volume, right? Number of moles per liter multiplied by the number of liters. That gives me these two numbers. You see that they are exactly equal. So at this point, we're at the equivalence point. All right. So what's the change going to be? Since we have equal amounts of these, they're both going to be consumed. So we're going to have negative 0.0010 moles, negative 0.0010 moles, plus 0.0010 moles, and the same thing here. And I don't care about chloride. It's just, if I was doing this myself, I wouldn't write it down. It's just because I'm your instructor, I'm doing it. So equilibrium, we don't have any of these left over, but we've got what? We've got ammonium ions, and that's a weak acid. I'm going to leave the chloride out just in the interest of time. We've only got 4 hours left. So if I divide that by the total volume, 10 plus 10 is what? Right? 10 plus 10 is 20 milliliters. So I'm going to divide that by 0.0200 liters, and I get the concentration of my ammonium ion is equal to 0.050 molar. You with me? Now what I'm going to do is I'm going to set up an ice table. Right? That's all I'm going to do because I have the concentration of my ammonium ion. This is something we've done now, what? Several billion times? I don't know. Maybe not that many times. We've done it a lot of times. Look, by now I'm hoping that you can do this partially asleep and partially awake. Okay? You've got an ammonium ion. You put it in water. It's a weak acid. It dissociates to give you ammonia plus hydroxide. You are starting out with 0.050 molar. Joel, this time I will have to work out that Ka, won't I? We have the Kb. We know that Ka is equal to Kw over Kb. I've already gone ahead and worked it out, and I'm sure that you guys can probably do it faster than me. Your Ka is equal to 5.6 times 10 to the negative 10 in this case. Anyhow, so we have 0 here, 0 here. We have a chain which is negative x plus x plus x. Again, our initial concentration of our weak acid is much greater than 100 times our Ka. So we're going to assume that x has no effect. So we're just going to write 0.050. Here we have x, and here we have x. Our Ka, which is equal to 5.6 times 10 to the negative 10, is equal to x squared over 0.050. We solve for x, which is equal to the concentration of, did I write this? Did I write hydroxide? Nobody stopped me on that. Surprise, okay? It's Friday. I am tired, okay? Hey, Jamil, all right. If I could give you a bonus point for that, I would. Hey, thank you. Okay, nobody stopped me. Well, Jamil did, I guess. All right, thanks. I appreciate that. So we have our concentration of our hydronium, square root of 5.6 times 10 to the negative 10 multiplied by 0.50. And I got 5.3 times 10 to the negative 6 molar. And so my pH is going to be equal to the negative log of that, 5.3 times 10 to the negative 6. And I get that my pH is equal to 5.28 at my equivalence point. Does this make sense? That I would have, that I would have an acidic pH when I'm at the equivalence point. Yes, absolutely. Even though all the strong acid is gone, there's none of it. Okay, what did you make? You made a weak acid, and a weak acid is going to lower the pH. All right. Now, in the end, the last step, when we're at 12 milliliters, well, then we're just going to have a whole crap load of extra HCl. And so our pH is going to drop a lot. We've got time, so let's do it. The last part. Okay. So now we're going to add 12 mils of HCl. Let's get going. Pitter patter. Let's get at it. We have our ammonia. we're adding HCl. And you know, the person who invented general chemistry too was actually a paper salesman. Did you know that? And the person also sold pencils, okay, and maybe calculators too. I'm teasing. And here, there we go. Plus chloride aqueous. There we go. So initially, we're starting out with 0.001. I'm getting tired of writing all these out. Hey, do you guys know how to calculate the number of moles of HCl? Because I don't feel like writing it out again for the umpteenth time. So it's 0.012 times 0.1, and you end up with 0.0012 moles. Okay, so you have none of these. I'm pretty sure you guys know how to do that by now. So I'm going to get rid of all of my ammonia, but I'm going to be left over with some HCl, won't I? Right? Plus 0.0010 and plus 0.0010. So at equilibrium, I have none of this. I have 0.0002 moles of HCl, and I do have my ammonium ion left over, and I do have my chloride ion left over. Well, so all I've got is HCl, ammonium, and chloride. Well, chloride isn't going to affect diddly squat, so I can leave that out. Now look, I've got a strong acid and a weak acid left over. Which one of these do you think is going to have an effect on the pH? The answer is the strong acid only. So really, to work out the pH in the end, I only have to consider the concentration of the strong acid. The concentration of my HCl is going to be equal to that 0.002 moles divided by the total volume, which is 22 milliliters, so 0.022 liters. I should have set this problem up to have 2 sig figs the whole way through. That's a mistake on my part, but anyhow, I won't make that mistake on your practice exam. So you end up with 0.0091 molar. HCl is a strong acid. Do I really need to tell you this again? The HCl dissociates completely into H plus and Cl, right? So to calculate pH, I just take the negative log of 0.0091, and I get that pH is equal to 2. I can't even read my own writing. So let's see here if I take 2.04. You know, I love these kind of problems because you can always ask yourself, does this make any kind of sense? If I've destroyed all of my ammonia and I've got an excess of strong acid, well, of course the pH is going to drop way down low, okay? Down to around 2. All right? Give me a thumbs up if you followed me through that problem. That was a long problem, wasn't it? Probably the longest thing that we've taken on, but it was 4 different parts. It's a 4-parter. That's even a word. All right. Look, again, it's the same things over and over and over. And if you were lost, if you're not following me, look, we're going to go right back to the beginning. Where the hell was I? It's right here. Okay. This is all we're doing is these steps right here. Okay. I'll review one more time just because I know that probably not everybody is at the same level here. So I want to go over it one more time. Look, if you're titrating a weak acid with a strong base, right, you do the neutralization so that you remove all of the strong base. Then you evaluate the new concentrations of the weak acid and weak base. And in this case, you would use a Ka, right? And you'd solve for this to get your pH. If you were adding strong acid to, if you're adding strong acid to a weak base, you're going to consume all the strong acid. You're going to be left over with some base and conjugate acid, and in that case, you would use a Kb. Okay, the same thing every time. Okay, and then you should know things like when the concentration of these are equal, that the pH is going to be equal to the pKa. When the concentration of these are equal, the pOH is going to be equal to the pKb, right? That kind of stuff. You should know what the equivalence point is, the half equivalence point. Well, this problem that we just spent the last 4 hours solving here, okay, what the hell would the titration curve look like? It would look like this, right? If you go from left to right, you're going to start out at a high pH, okay, not above 12 because you're titrating a weak base with a strong acid, okay? Your equivalence point is not going to be at a pH of 7. Your equivalence point is going to have a pH below 7. It's going to be acidic. Why? Because at that point, you will have neutralized all the weak base, but you will have created the conjugate acid, which is going to produce hydronium. And then at the end of the titration curve, it's going to drop below 2 because you're adding a strong acid. So again, at the pH at equivalence point, it's going to be lower than 7. It's not equal to 7. That's a strong acid and strong base. Before you reach the equivalence point, this is the buffer region. If you want to use the Henderson-Hasselbalch equation in the buffer region and you're confident, go for it. If you need to make an ice table, go for it. Okay? You use whatever works best for you. Okay? After you reach the equivalence point, well, then you're just adding acid, strong acid, so the pH is going to drop steadily. Curve isn't symmetrical. The half equivalence point, we talked about that is, it's half the amount of acid to reach the equivalence point, just like it was in the last one. And then when you're at the half equivalence point, okay, at the half equivalence point, just like the titration of a weak acid with a strong base, except here your POH is going to be equal to your pKb. Okay. All right, there you go. I think that in the interest of time, we've only got 11 minutes yet. 11 minutes left. We're going to come back to question 39 if we have time. I just want to talk about indicators briefly. I'm not going to quiz you, with 1,000 questions about indicators. Has anybody here done a titration in the lab where they used phenolphthalein as an indicator? It's a very common indicator when we use yeah, there we go. Okay. So yeah, phenolphthalein is a really common indicator, and the structure of it is shown here. So again, I told you what an indicator was at the very beginning of the class. Today, I said an indicator is some kind of molecule that you put in a very, very tiny amount, usually a drop. You can even use a half a drop, and it will totally work. The indicator is going to be colorless, or usually some of them will exhibit a color, and then they're going to change a color or change color over a certain pH range. So basically, when the titration is complete, when you've reached the end point, the indicator is going to change color. So you want to have an indicator that changes color down here at the bottom. You want to have an indicator that changes color around the end point, okay, of the titration. Now there's some math here on here. I'm not going to ask you about the ratio of the conjugate base to the weak acid because most indicators are in fact weak acids. Like phenolphthalein, I'm sure you've probably never looked at the structure in the lab. Maybe you did, I don't know. But you can see that if you add hydroxide, it makes this conjugate base here, which is pink. So when you've added enough base that you're at the equivalence point, it should turn faint pink. But then if you add more and more and more, it's going to turn dark pink. The color transition of a pH indicator is going to occur around plus or minus 1 pKa unit. And, I went over this with you earlier in class, but in case you didn't follow me then, what are the ways that we can measure pH? You can use a pH meter. I told you I'm not, Mr. pH meter. I'm not an expert at those, and I'm not a huge fan because I find they're pretty, they have to be calibrated and such. But you can use litmus paper. I mean, I'm an organic chemist, you guys. That's what I did most of my adult life, is work in the industry as a organic chemist. So I never had to use this, okay, for the past how many years I worked 15 years in industry, okay? But I use this every day, okay? Just simple pH paper to give me a quick qualitative assessment, okay? So that's kind of my cup of tea. Also, if you Google hydrangeas, you can actually use hydrangeas as a pH indicator, because if they're grown in acidic soil, hydrangeas turn this beautiful blue color. And if they're grown in more basic soil, like a pH greater than 6.5, I think, then they turn this color here, this red color. Has anybody ever done this experiment in high school where you boil red cabbage and you take the red cabbage juice and you can use that as a pH indicator? Has anybody done this? It works really, really well. And in fact, we do it here at UCCS with students who are in nursing chemistry. They actually do this experiment. They take cabbage juice, okay? You can try it at home. Just Google it, just say cabbage juice pH indicator. It works really well. And you see the range of colors is freaking good, for something that costs, pennies to try. So when you have a really basic solution, it gives you this kind of yellow green, then it ranges all the way down here to red for really acidic. But if you're the kind of person who likes to try experiments at home, you can try it. You can try the red cabbage extract experiment. Really simple. You just need to buy a red cabbage. How much is a red cabbage these days? I don't know. Anyhow, but the more nuts and bolts about what you guys are interested in are looking at pH curves. I have two different curves here, and being able to choose a good indicator. Okay, so it says here many indicators can be used for the titration of a strong acid and a strong base because the vertical area is so large. The answer is this, okay, to what you're going to be asked on an exam, and I'm sorry that it's cut off here. Okay, can I hold it like that? Draw on it? No, I'm trying it. Son of a gun. No, it won't let me do it. Crap. I'm sorry that I have this so far on the side here. But let me get the highlighter and try doing this. Okay. The indicator that you choose has to have the color change on the vertical part of the curve, okay, where the vertical line is. Okay. Now this one is the titration of a strong acid and a strong base. So you can use a bunch of different indicators. It says here methyl red. Our textbook calls it methyl orange. It's the same damn thing. I just took these pictures from a different book, I think. And then you could also use phenolphthalein. So again, strong acid, strong base, you can use a whole holy host of indicators. However, what if you were titrating, doing this titration here? This is a weak acid with a strong base. How do you know that, Mr. Dion? We went over this already. But look, the pH is starting above 2. Okay, so it's below 7. It's acidic, but it's a weak acid. But look, I told you that the indicator has to change colors around the vertical part of the line. Right? You can see that methyl orange is going to undergo a color change. It's going to go from red to yellow, right? But it goes red to yellow over this pH range here, which is not near the equivalence point, right? It goes over, from what, maybe 4 point something to around 6. But my equivalence point is up here at 8, okay? But you can see that the phenolphthalein does undergo the color change at the vertical point, the vertical part of the titration curve. So again, this is just me rehashing the same old stuff. The end point has to be as close as possible to the equivalence point. This is a whole list of different pH indicators. I will not ask you to memorize. I don't think I do. I'll have to double check my practice exam. I'd have to look at it again. The few questions that I picked out. But you don't have to have these memorized, but I think that what's cool about this is that you can see, first of all, how many different indicators are out there on the market and how they all have their place, depending on the endpoint of your titration. Now, there's one more picture in here. This one comes from our textbook, too. Look, this curve here is strong acid and being titrated with a strong base, right? This curve here is a weak acid being titrated with a strong base. We looked at both of these today. Now, notice that their equivalence points are different. But remember, the indicator is only good around the vertical part of the curve. But you can see that the strong acid plus strong base has a much bigger vertical point. So you can use either phenolphthalein, methyl red, or what we call methyl orange in our textbook, or you can use litmus paper will work. Whereas if you were to use or do the titration of a weak acid and a strong base, that's this curve here. You can see the vertical part is only around here. And so the only indicator that's going to work would be phenolphthalein. Now, a picture is worth 1,000 words, and to me, so I put in this picture, which I don't think is in your slides. This is one I took from the textbook called CHEM, which is a really famous general chemistry textbook. Some of you might have used it in a high school class or something like this, but I thought you did a really good job of focusing in here. This is the titration of a strong acid and a strong base, and he shows you why you could use phenolphthalein, right, because it lies in the vertical part, why you could use methyl red, which is the same thing as methyl orange, and then litmus would be somewhere in here. But if you go up to this list of indicators up here and you look up thymol blue, right, thymol blue changes color between what? Around 1 and 2 and a bit. So thymol blue does not land in that vertical part of the curve, so it would not be an appropriate choice. I just saw that last night when I was preparing for this lecture, and I thought it was a really valuable slide, or picture, so I put it in here for you. Okay? Anyhow, that brings us to 1038. So there you have it. I put some problems from OpenStax, and those are just ones that are already listed on Canvas in your list of suggested practice problems. Okay, there we go. So